Okay. So I think let's go over the assignment. I think that'll be a good place to start. So
This is the first time I've written by hand in a while. That's all I have to say.
nice. Okay, hopefully you'll do the assignment. If you didn't, well, maybe you'll get a crash course on it now. But here we go. We're just gonna go rapid fire in a circle. I'm gonna point at you or call you out and you're gonna answer the question. And then we can discuss it if there's questions. So, Shri, can you compare the pros and cons of a linear power supply and a switch mode power supply?
Sure. So a linear supply, basically it's low noise since there's no switching on and off, unlike the switch mode, obviously, which also has an inductor, which means that it's high noise. And then the linear supply is also lower efficiency since like, I guess like everything you're not using is like thrown away, I guess. And then it's also a simpler design because it only has like a few components, and it's compact because it has fewer components, and it also gets hotter. I guess one of the reasons is also because it's smaller, so there's like less surface area that the heat could dissipate through.
Okay, do you mind if I ask you some more questions about what you said?
Sure.
So you said an inductor necessarily means higher noise. Why is that?
Because when there's current flowing through an inductor, it generates a magnetic field, and because of the magnetic field, you get some EMI.
Nice.
Green vocab word.
Yes. You also said surface area.
Also,
Yeah.
I have a question about efficiency. I don't know if I understand it well. So can I like tell you what I understand if that's like right?
Yeah, sure.
Okay, so basically if you have a buck converter and like a linear supply, and you give them the same input voltage, same load, then what I understand is that basically the linear one consumes more power because it draws more current, which makes it less efficient since it's consuming more of the power and supplying less. Is that right?
Kind of. Do you mind if I just sketch something out for you? It might help.
Yeah.
Okay, I'm going to share the whiteboard. Can y'all see the whiteboard? I can't even see the whiteboard. I hope y'all can. Okay, can y'all see the whiteboard?
Yep.
Yes.
Okay, cool. So we have a battery or a power supply or whatever, right? And this is grounded. And then let's call this our linear regulator. And this is our load. Yeah. This is also grounded. And then let's look at a buck. We have this. Switch, diode, ground, inductor, capacitor. It's getting progressively more ugly, and resistor. Okay, y'all get the idea. So assuming that these are the same, these two inputs are the same, and these two loads are the same, we're claiming that the buck converter will have a higher efficiency than the linear regulator. And the reason for that is we can use this equation. So efficiency represented by N, or like this weird gamma symbol, equals power out over power in. What's up?
I think I'll hear you below your decibels.
Okay. Okay, so power equals voltage times current. And we know that our output voltage and current are the same because the load is the same, which means that there's some difference in efficiency or current here and here. Sorry, I got distracted and I lost my train of thought. The sources for conduction loss, or just losses in your buck converter versus your linear regulator, are different. So in your linear regulator, all your energy that you're not using is... Bro, shut up. All right.
You're talking too loud. I'm in a meeting too. You should have told me to wait till dinner. God damn it.
There's so much chaotic energy in that house.
Wow.
No, you.
Okay, so in your linear regulator, you're dissipating any excess energy just as heat. It's like, so if we express this linear regulator a different way, like a voltage divider, that means that you're experiencing a lot of conduction losses through the second resistor. So we have a voltage out here. And whatever voltage we're not using is going through this resistor, just like away. Yeah. We don't experience the same magnitude of conduction losses in a buck converter because when we're not using excess energy, the switch is open, right? We do still experience conduction losses because when the switch is closed, there is some non-zero resistance across the switch. It is much smaller than a resistor because a resistor necessarily resists, whereas a switch is much lower resistance. Also, when we're in the open state, when the switch is open, and we have current flowing like this way, basically, there's conduction losses across this diode.
Yep.
So for a diode to work, you drop a voltage across it. And that necessarily means you're losing power through conduction. That is conduction losses. For the switching regulator, there's also another source of losses called switching losses, which you might be familiar with, which I briefly touched on in the video. I could draw a little graph here. So this is time, and then I'll use some different colors. So let's tell voltage red. Okay, so when your switch is closed, your switch is off, the voltage across it is very high because you have like 5 volts and 0 volts. These are like different voltages and current can't flow through. So you start at a high voltage and then you turn on the switch. So you close the switch, current can flow. That means that the voltage between these 2 points, there's no potential difference. It's the same voltage. So it becomes very low. But that doesn't happen instantaneously. In a perfect world, yes, but in the real world, like it'll slowly like hit very low. And then it'll hover at this value. And then let's say you turn off the switch, it'll go back up after some time. So this is voltage.
Wait, sorry, I have a quick question. So I guess, yeah, another thing I didn't understand was why is it that when the switch is off that there's a higher voltage difference? Because
yeah,
I would think that when there's current flowing, that the current flows because there's a higher voltage difference. So, and when a switch is off, there's no current flowing. So I just didn't understand that part.
Yep. Let me just draw this here. Very simple circuit. Let's say this is 5 volts and this is ground. Yeah. So these are not connected. Actually, let me add a resistor for this to make more sense. Since this value is like floating and there's no potential difference across this resistor, this value is 0 volts. And since this value is floating, it's immediately just going to tie it to this 5 volt value. But let's say we close this switch. all of a sudden there's like this path for current to flow. And that's through here, right?
Mhm.
And the way that voltage drops works is you start with some voltage, V in, and then you hit ground. And it's proportionally dissipated through your resistances, right? So if like this is a big resistor, you'll drop a lot of voltage here, and you'll drop the rest of it across the little resistor. This is a little resistor, you'll drop a little bit of voltage and then drop all of it, or most of it here. So in this case, our switch has very little resistance. So you're gonna drop all 5 volts across this resistor. Does that kind of make sense?
Yeah.
So now, since we know that this is 0 volts because it's ground, and we lose 5 volts across this resistor, how much resistance will you see at this point? Or how much voltage will we see at this point? Sorry.
Oh, sorry.
So-
Are you asking?
Yeah.
What's the question? Sorry.
Yeah, you have 0 volts at ground,
Mhm.
and we know that we're dropping 5 volts across this resistor.
Mhm.
So how much voltage will we see at the top of this resistor?
5.
Yep. So when we have a closed switch, we see 5 volts on both sides of the switch. Whereas when we have an open switch, there's no longer this voltage drop, and this is 0 volts. And since voltage is a potential difference, the potential difference between these 2 points is 5 volts. Make sense? And yeah, and to be more clear, there's no current flowing, but you don't need that. Okay.
Thank you.
Yep. So coming back to this graph over here, we have our voltage, and our current basically does the opposite thing. When the switch is open, there'll be no current flowing, or like very little leakage current. Don't worry about that too much. Very little current. And then when you turn the switch on and current can flow, the current ramps up. And then when you turn the switch off, current ramps down. What is important to know here or to remember is that P equals IV. And when you have a positive voltage and a positive current, those two numbers multiply together and you have some power in these sections.
Nice.
So you're losing power there. And that's called switching loss. So in a linear regulator, you won't see this kind of behavior because there's no switch. So there's never that transient when your voltage is going up and your current is going down, or current's going up and voltage is going down. But in a switch mode power supply, this is something that people are very wary of. So in a switch mode, you have to worry about conduction losses and switching losses, whereas in a linear power supply, you only have to worry about the conduction losses. Make sense?
Yep.
Cool. And feel free to stop me if any single thing doesn't make sense, because we want to make sure that our foundations here are very strong so we can build on it. It's okay if you ask me how a resistor divider works or anything. I don't care. I want to make sure that we're all on the same page. Okay. Back to this. We kind of addressed this with here. All right, Izzy, what's the simplest form of a linear regulator?
Is that just okay? Yeah, I didn't exactly know what this meant. If that was like, because I saw the picture drawn out. I even drew it out, but it was like they have the little like thing and then the two capacitors, and like that was it. So I wasn't sure like if that's what that meant or.
Yeah, I'd say that's not the simplest, because there's like, you have to worry about the silicon inside the IC and all that. Like, what is like bare bones day one ISIM linear regulator? How do we get 5 volts to 2 volts or something? What can you use?
Resistors.
Yep, exactly. So,
Okay, cool.
yeah. I hope you all found links. We could go through those later and talk about the selection process for chips. But just keep
Oh wait,
those.
I had a hot question about that. If we want to touch on it later.
Go for it.
When I was going through like the filters of like DigiKey,
Yeah.
so it had so like input voltage was 6 volts, but then it said output, and then it was like output min and like output
Yeah.
max. So where were you supposed to put 5 volts to?
Usually when I look for components, I put it within like a range because the way that suppliers list their components is not always the same. It gets kind of annoying. So I just picked a bunch, or I would pick a bunch for your input and your output min and your output max. And then you'll have to do a little bit of parsing yourself and say, okay, this looks like a good one. That'll give me 5 volts or whatever. It's a little bit of extra legwork on our part, but it makes sure that we don't miss something that might be good.
Makes sense.
Okay. We just drew a simple buck converter. All right, Adi, what's the point of the switch?
The switch basically allows you to control your the duty cycle, so you can turn it on and off at whatever rate that you want, and that allows you to actually set your output voltage.
Yes. Perfect. What is the equation for input voltage, output voltage, and duty cycle?
I believe like duty cycle is like percent that, so it would be like duty cycle would be output over input times 100 or something, divided by 100, one of those two, something like that.
Yeah, I mean the duty cycle can be, it can be a fraction, decimal, or percent. It's all the same, but yeah. Cool. All right. Izzy, what's the purpose of the LC filter?
So that's so since you're switching it on and off, it's you explained it as bumps between, so it's going from 12 volts to 0 volts, and it's a lot of almost like noise. So you're trying to clean up the signal to make sure that like you're getting a smooth signal instead of like rapidly changing back and forth.
Yep, pretty close. We're still rapidly changing back and forth, but the peak to peak is much smaller now.
Right.
The rapidly changing never changes, but like we could kind of trick.
Yeah.
The
You're trying to
component.
trick it. Yeah.
Exactly. All right, Tree, what's the purpose of the diode?
So there's some voltage that, well, I guess like going back to inductors, I believe this is caused by self-inductors, but basically like when you have the switch on, then there's current flowing through the inductor, and then that generates a magnetic field. And then basically like when you open the switch, because of the way like voltage, current, and inductance are connected, basically you get a negative potential because you have because like technically you're like stopping the current flow, so then it's like it switches the sign of the voltage, and so that I believe that's like the voltage that you don't want, and that causes a spike in the load, and basically like to dissipate that energy you use like the freewheel diode, and that kind of gives you that like little like low resistance path that you showed earlier.
Yep.
I don't know if any of that made sense, but
No, yeah, that was pretty close. So your inductor is building up energy in the form of a magnetic field. And we'll talk about capacitors in a bit today, but inductors and capacitors are kind of the opposites of each other, or like inverse. Or don't worry about that. They're both energy storage devices, but they behave differently, or almost the oppositely. So capacitors don't mind changing currents, but they hate changing voltages. Inductors don't mind changing voltages, but hate changing currents.
Yeah.
And when you open your switch, all of a sudden no current is coming in. So your inductor's like, whoa, what the fuck? Like, I want current to keep flowing. So it's going to convert that magnetic field. That magnetic field now has a path to convert itself into electrical energy, where it then takes the form of current and flows through your circuit. The diode is like Shri said, our path or low resistance path for dissipating that excess energy because we don't want it in our system. Yeah, I think that a really nice way, or at least what helps me a lot with understanding capacitors and inductors more intuitively, is that A, they're both energy storage devices, and then knowing which one of them likes changing voltages and doesn't like changing voltages, which one of them likes changing currents, which one doesn't like changing currents. That helps you remember the equations for them also. So, yeah. Okay, Adi, name a couple of types of buck converters.
Okay. I mean, you can, okay, I don't actually have a good answer to this one, but you could specify the different types of buck converters based on like their properties like thermal efficiency and like their different voltage ranges. Yeah, that wasn't the answer you were looking for. So
yeah, I've never really heard them described like that. Maybe they are, but I don't know.
All right, go for it.
Yeah, there's like a few types. So like you could have a regular asynchronous buck converter with a single switch and a diode. Here, it might help if I just draw these and then we could, whiteboard. Okay, can you all see the whiteboard? So like an asynchronous buck converter is you have a V in and then you have a switch. And then you have your diode. And then you have your inductor, and then you have your capacitor, and then you have ground. You might notice that like I kind of draw buck converters differently every single time, and that's because that's how I feel is convenient each time. They all mean the same thing. If you want to draw this line, you can connect all the grounds. If it makes you happy, you can do that. Or you could remove these little ground symbols and make it one big square. But yeah, like they all mean the same thing. If they don't, I'll make sure to tell you. But yeah, this is an asynchronous buck converter because there's only one switch and it can just do its thing. There is something else called a synchronous buck converter where you have two switches. And I'm using the word switch very liberally here. They're like MOSFETs or GaN FETs or some type of switching device, not like an actual switch, but I'm sure y'all could come to that conclusion. So this is like a synchronous buck. Those are more complicated because you have to control two switches and make sure that the timing of the switching is correct. What this switch provides, the second switch, it takes the place of the diode. So in the diode, you'll experience higher conduction losses because you're dropping voltage across the diode every single time. Whereas with this switch, it's like lower energy dissipated across the switch. It has a lower like on resistance if you think about it that way. So in a sense, they're more efficient, but also they're more difficult to get the control logic for. That's not really a concern for us because most of the chip manufacturers do the hard control logic for us. Other considerations is there's more noise because you have something switching. There's more heat generated because you have a lot of switching. There's ups and downs.
Real quick about the synchronous buck, shouldn't it still like in theory have the same efficiency because, or I mean, yeah, the same efficiency because it still has to drop the same voltage spike that was caused by the inductor, right? Just like the diode, I mean, both the diode and the second switch serve the same purpose and they have to drop that voltage spike. How does this one achieve like a higher efficiency?
Good question. We don't necessarily need to empty out the inductor every time we turn off the buck converter. So the inductor is trying to empty out the magnetic field when there's no current flowing. But as soon as we reintroduce the current, the inductor is happy and the magnetic field starts to grow again.
Yep.
So
the switch like kind of does the job of the diode, but like less intensely. I mean, kind of
less unefficiently. So like more efficiently.
Yeah. Okay. I can kind of see that. Sure.
there's also like stuff like multi-stage bucks where you have like a different switch with like different rates with like different inductance and capacitance values. And this voltage out is different from this voltage out.
Damn.
That like there's a lot of stuff. There's also stuff like there's boost converters which convert a lower voltage to a higher voltage, and there's topologies called the buck boost converter where
Yeah.
it mixes both of them. And the math and
What's the boost? This boost like significantly
it's
Yeah.
all the same parts. It's just configured differently.
Oh yeah. Okay, I saw that somewhere. Yeah. It's
Yeah.
like you flip like. What do
You
you
just rotate everything.
flip?
That does makes zero sense. So I'm just going to not talk about it.
Damn, I thought you were gonna draw it out for us.
No. Let's talk about bucks for now. We could talk about boost converters in a later day.
All right.
Okay. Did anyone figure out how the feedback pin of a buck chip works?
Google knows.
If
I
not,
like tried to look it up. I don't know if what I found was exactly accurate.
I straight
Um,
up told myself I'd go back to that question, never did.
okay, nice. I could just annotate here, I think. There's like a short answer. I'm going to give you a very big hint. So this is a voltage, and like this is a number. This is what I need to know. This is the answer to the question.
What?
I just need a number.
5.
You want me to give you a number? 0.
12.
Wait, does the feedback pin just like take in
42.
output voltage?
So let's think more generally and say, okay, I could use this buck chip to take 12 volts and step it down to 5 volts, but I could also take 12 volts and make it 3 volts. I could also make 12 volts, 7 volts.
Yep.
So we can use the same chip to achieve different voltages.
Yep.
Now, this pin, which I'm referring to, is called a feedback pin. What are we taking the feedback of? Are we taking the feedback of the input voltage or the output voltage?
Probably output.
Output.
It's the output. We don't give a shit about the input because the input's going to do its thing, but we want to make sure the output is a solid 5 volts or whatever, right? But what if we want it to be 7 volts? What if you program the buck converter differently? We use hardware to program it. But yeah, basically there's a feedback pin that does the same thing no matter what output voltage we choose. And it does it with a pretty clever way, in my opinion. So let's say we have our buck chip, and then we have our inductor, and then we have some capacitance, and then ground, and then your load, right? This is, like the switching is happening in here, so don't worry about that. This node is called V out, right? What can we say about the voltage here, 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 and here?
It's the same.
Yep, this is all the same net.
Yep.
If you remember Kirchhoff's voltage rule, like if you have a voltage in and like a bunch of different branches, these will all be the same, and then they'll all meet back up and it'll all be the same over here. And yeah, let me erase this. Okay. So let's pretend V out equals 5 volts, right? And let's say we have our feedback pin over here because we said we care about the output voltage. This is a tough question, but what can we do between this 5 volts here and this feedback pin to make sure that, what if this was 7 volts? The feedback pin is still happy. Like, the feedback pin's not very smart. It doesn't know what we want, but we know what we want.
Is the feedback pin like looking for like 5 volts, or like in order to make it happy, it's looking for 5 volts?
Very close. It's looking for a voltage. So what's actually happening is we have a resistor divider with an output that goes to your feedback pin, and then the rest of it goes to ground. Wow, that is not even close. Okay. It usually is about 1 volt, because if your buck converter is going from 7 volts or 5 volts or 3 volts or whatever, like if you think about it, if your feedback pin is looking for 5 volts and your output is 3 volts, you're not going to be able to reach those 5 volts easily. It'll be pretty cumbersome. I don't even know if you can, right?
Yep.
So it wants a very low voltage that's consistent. So if we are getting a constant 5 volts out or whatever, we do a resistor divider, we dissipate 4 volts here, we dissipate 1 volt here. So that means that 1 volt is reaching the feedback pin at all times. And you remember how Audley said that the duty cycle changes depending on the output voltage? If you want a higher output voltage, the duty cycle will be higher, meaning that the converter is on for longer. Or if we want the output voltage to be less, we make the duty cycle shorter. That's basically what the feedback pin is doing. It's taking in the output voltage and saying, how close is this to 5 volt? Or, I misspoke. How close is this to 1 volt on this resistor divider here?
Yep.
And if it's greater than 1 volt, it's going to say, I'm going to back off on the duty cycle. If it's less than 1 volt, it's going to put some gas on it, and then it's going to increase the duty cycle.
Gotcha. So it's our job to set those resistor values based on the actual output voltage that we want.
Precisely. The data sheet usually does the math for you there. But yeah.
Cool.
What's nice is that the feedback pin is usually a high impedance input. Do you all know what high impedance inputs are?
It doesn't draw much current.
Yep. High impedance means that like there's like a big resistor here, like a big old resistor. That is a terrible drawing, but I hope you'll understand what I mean there. Which means that the resistor math here is a lot easier. Like there's no risk of some current dropping here and some current dropping here, and then this node is pulled to like some weird value, and yeah. Okay. That aside, does everyone think they understand how the feedback pin works? Tell me in one sentence what the feedback pin is looking for. Shri.
Basically, so say you wanted an output of like, yeah, I need to.
All right, the feedback pin is looking for one thing only. What is it looking for?
Love.
There's a value.
Yeah.
There's some,
the 1 volt.
yeah, exactly.
Gotcha.
It's
I
looking
thought you
for
wanted me to explain like the whole process. I was like, bruh.
Okay, let's talk about the whole process. How are we reaching that 1 volt? What's happening? I'll draw this again. So we have this, and I'm going to skip all the details, and we have 5 volts here. And we have our feedback pin here, which is looking for 1 volt. And then we have like ground here doing something. How is this happening? What happens between here and here? What components can we add to make this 5 volts into this 1 volt?
You trying to add another buck converter?
You only need.
I'm just joking. Yeah.
I was like, my guy. Oh my gosh.
I mean, you could, but like that would be wild. So what can we add here? You need 2 of them. Starts with an R. And ends in,
It's
Oh wait, were you asking me this whole time?
yes.
Oh,
Yeah.
I like. Okay, a resistor. I'm gonna guess.
Yes. Great guess.
Oh, I'm okay.
Yeah, and then you can achieve this 1 volt. Okay. Hopefully this is demystified a little bit. Let's move on. Why do we put capacitors on the input and output of power supplies? What do they do? Izzy.
They filter the signal.
Okay, what happens when we have like changes in our input or output voltage? How do the capacitors work?
Well, I don't know if this goes into the next question, but that if there's too much like voltage, then the capacitor will hold some of it so the correct amount flows. And then yeah, is that okay? Yeah, and then if it's not enough, it will give off some of the energy so that the correct amount is always present.
Precisely. The correct amount of what?
Voltage.
Yes. What do capacitors like and what do they hate?
They like
Or I guess like that's the same thing. Like what do they hate?
they don't like changing voltage.
Yes.
Just
Okay. Why do we put multiple capacitor values in the input and outputs of power supplies? And there's a really cool thing I want to show you all after we go through these questions. That'll really maybe show you something cool or leave you very confused, but I think it's cool. Adi.
Different capacitors for different frequencies.
Yeah.
Yeah, filtering basically.
Would you use a higher or lower capacitance for a higher? This is a terrible question. Would you use a higher? Would you use bigger capacitance value for higher frequency or lower frequency?
Yeah, so I'm gonna actually phone a friend, and I think she got this one.
way to pass off that question.
Oh, why is my phone ringing?
Oh, yo, what up, dude?
Yeah. If anyone wants to take a guess, they can. I'll just tell y'all, and then we'll explain why later. But
I feel like this has something to do with the graph that you showed us on the slide.
yeah,
And they all superimpose, and then it's really low
yeah.
when it's at like 1
Wait,
megahertz.
actually, if it's your equation would just be like frequency is 1 over r times c, right?
Mm,
No?
that's like a cutoff frequency.
Oh, that doesn't actually. Nah.
That tells you where like the filter like dips.
Damn. All right, what you got?
Bigger capacitance means you want it for lower frequencies.
Okay.
So you want the smaller capacitance values for higher frequencies closer to your chips or your supplies or whatever.
Got you.
If you read the Eagle document, they kind of talked about that briefly. Oh, also, what did y'all think about the stuff I prescribed? Was that like too in-depth, like too light, or like, can y'all handle a little bit more?
Yes.
Yeah, go for it. Yeah, it
Yeah.
was good. I would,
Okay.
yeah, I would add like maybe one more like in-depth article.
Okay,
Just-
yeah,
But yeah, no, that was good.
sweet. Okay, I don't remember who's next in line.
I think it was me.
Okay, what can we include in our converters to protect against overcurrent events?
I believe a fuse,
Mm-hmm.
which basically like is something that melts when too much current goes through it, so it stops the current flow.
Yes, that is one type of fuse. There's another type of fuse. Do you know what that is? There's a 3-letter acronym for it. And anyone can answer this.
EMI. No, I'm saying like the inductor counteracts the current spikes, and then it creates EMI. Like you kind of see what I'm saying?
I mean, yes, but no.
Does it start with an H?
No. It's a PTC fuse, and that stands for positive temperature coefficient. So what happens is, like in a traditional fuse, you have like your little filament, which is basically a really thin, tiny piece of metal, and the metal will break when a certain amount of current flows through it because it gets too hot, and then the metal's like, nope, and it's done, and that's how it breaks. But those are not reusable. You literally have to like remove the component and put a new one back on, whatever, right? It's kind of annoying. So the cool thing about PTC fuses is that they're basically fancy resistors. I like to think of it as fancy resistors. So this is temperature, and this is resistance. So current is directly proportional to temperature, as you may or may not be familiar with, which means that as the current increases, the temperature will necessarily increase. So at low temperatures, the resistance of the fuse is very low. Like we don't want it to be doing resisting. We want it to be doing fusing, right? But then what if the current is getting higher than we want it to and the temperature is rising? Well, the fuse is going to say nope, and then it's going to the resistance is going to be massive. The cool thing here is that the fuse doesn't actually break. It just becomes like a massive fucking resistor, which means that current cannot flow through it anymore, or like a lot of current cannot flow through it. Eventually the component will literally break and fail, but like you will long before like not see that problem. Like the fuse will do the fusing.
Nice.
Yeah, so that's the other kind. That's what we use on our buck converters in formula. If we find that maybe PTC fuses aren't good for bucks, maybe we can change it. But I think, at least from what I know, they seem fine. Okay, next, Adi, what can we do to protect our converters against overvoltage events?
I would have said capacitors, so I'll just stick with capacitors.
Yeah, I'd say capacitors would work for very brief overvoltage events that are within like the range of what your capacitors are rated for.
Yeah.
There's something
I
we
don't know
do.
about linear spikes though.
There's something we have on formula as like protection. Do you know? Does anyone know?
What I
Zener
looked up.
diode.
Yep. What do you say, Z?
Yeah, I was gonna say I looked up and it said like rectifier. Not that I exactly fully understand what that is, but
Not quite. A rectifier is something a little bit different, but Shri was, yeah, hit the nail on the head with Zener diode.
Oh, yeah.
nailed it.
Oh, yeah, we learned about this. Yeah. It's good
You'll
stuff.
see this guy over here is a Zener diode. Okay,
Yeah.
I see. Thank you for telling me this time. This is a Zener diode.
Oh,
Solid.
she's kind of cute.
Yep. So there's something else I wanted to talk about today. I wanted to talk about capacitor selection. So let's talk about that. And then we could talk about like Zener diodes and overvoltage protection next week or something else. But we could come back to this. I'm excited to talk about this graph that was in the Buck presentation. And I understand it much better than I did when I actually gave the Buck presentation. So I feel a little more confident actually talking about it this time. So let's talk about it. Can you all see the whiteboard?
Mhm.
Okay.
Yep.
I'm going to draw some lines. Oh man. Let's do black. And then my God, that's a nice graph. Okay.
I know.
And then over here, let's have frequency. And over here, let's have impedance. Yeah?
Yep.
Okay. Y'all may remember this from ISIM. If you don't, it's totally okay. What is the complex form for a capacitor of a capacitor equation?
Aha.
Oh.
Buddies has some great jokes today.
Okay. Well, I'll just get to it then. So let's start with a resistor. This is an easy one. What is the impedance of a resistor?
R.
Yep. The impedance of a capacitor is, I'll give you a hint. It's 1 over something. And that something has to do with capacitance and frequency.
I hear typing.
Oh, yeah. Okay.
Sorry, I didn't mean to call you out, but
It's okay. We all heard it.
I feel like this has to do with the big green sentence that said impedance is resistance at different frequencies.
Oh yeah.
I mean, yeah, but like, okay. What is something that a capacitor has? What is a very characteristic thing that a capacitor has?
Capacitance.
Yes. So that's one thing.
Dope.
And we're talking about frequency. Do you think we should talk? Do you think frequency goes in here somewhere? Maybe in this gap?
Definitely.
Oh, the period.
Yes. So I'll use omega to represent that. And then when we're working with complex numbers, we just like to throw in J's everywhere, right? So that's
Nice.
just,
Oh, I vaguely remember this.
yes. So this is how a capacitor behaves at different frequencies for a given impedance. Okay, whatever. Inductor, I'll just give it to you because you'll probably didn't talk about it in ISIM. It's J omega L. It's like the opposite. Okay. So now I'm going to draw what a capacitor really looks like in real life. So you have your ideal capacitor, right? But it's inside like a ceramic package or whatever, right? And like I harp on every single time, everything has an equivalent series resistance and inductance and capacitance. So there's a real resistor over here, and there's a real inductor over here. I hope y'all could tell the difference, but you'll know what I'm talking about. So that means that we're dealing with all three of these things at the same time when talking about capacitors and their impedance at different frequencies. Okay. What can you tell me about the proportionality between impedance and frequency for a capacitor? Are they directly proportional or inversely proportional?
Inversely.
Inversely.
Yes, they're inversely proportional. So if the frequency is increasing, how is this Z going to go? Is it going to go up or down?
Down.
Yes. Perfect. So I'm just going to draw this. So this is our capacitor part of our capacitor. Eventually, depending on this inductor value, the inductance is going to pick up somewhere. What do you, like what direction do you think the inductor is going to go? Is it directly proportional or inversely proportional?
Directly.
Yep. So at some value, we're going to have an inductance going up. Ideally, you want this inductance to be like here somewhere. And I'll talk about why in a minute, but I'll just erase this first line to make this point a little clearer. Finally, we have a resistance, right? Is this directly proportional, inversely proportional, constant? Like, what is it? How does R change or Z change with a changing omega given an R? Does it?
Constant.
It's a constant.
No, it doesn't change.
Yep. So we just draw this here. So this is what our capacitor really looks like. And if I were to draw it with like a new line, it's like that.
Gotcha.
There are different things we could change to make this curve the way we want it. But at a high level, the goal is to minimize the impedance at all points of operation. So our switching converter operates from this arbitrary frequency to this arbitrary frequency, right? Which means that we want the impedance to be as low as possible in this area.
Yep.
And I don't think we can accomplish that with one capacitor because it looks like this one picks up over here and the impedance gets pretty high within our range. So what do you think we can do?
Slap another one on there.
Yeah, exactly. We can slap another one on there. So let's say I want to move this capacitance curve, this part here, to the left. What can I do? What should I do?
Wait, to what?
What can we do to the capacitance to move this to the left?
Would you increase it?
Yeah, yeah, precisely. We'd
Sorry,
increase
there
it.
was a there was a moth on my table. I just got distracted. Sorry.
Okay, cool. Yeah, moths are pretty bad.
I was just confusing myself. So
But when we have bigger capacitance values, you know what happens to our capacitors? Do you think they get bigger or smaller?
Bigger.
Yep, they get bigger. And if our capacitor suddenly grows, what happens to our inductor? Does it grow or shrink?
It'll grow.
Yeah, the inductor grows because there's literally more material that acts like an inductor. So now, when we increase our inductance, what happens here? Does the curve move to the right or I'll just give you a hint, it just goes this way. But also what happens to our resistor? Does it grow or shrink?
Grows.
It grows. So all of a sudden this constant's higher. So now this new curve is looking a little bit different, right?
You're off of one of the blue lines.
Oh yeah, sorry, thank you. Basically, we're playing a game of minimizing with the size of our capacitor, the size of our capacitance, and these like parasitic values. Eventually, when you have a bunch of nice capacitors, you'll have like curves that look like this.
Yep.
And let's say that our operating frequency range is from here to here. What our superimposed graph, when you add all the impedances, because current will take the path of least impedance or resistance always. So it doesn't matter which part of the capacitor or the circuit has the least impedance, it'll go through there. So all the current sees is something like this.
That's nice. Would you put these capacitors like you just this is specifically for like decoupling or bypass capacitors? Yeah. Or I mean, I guess it could.
This is more useful for input and output capacitance on a power supply. Most chips and ICs, you need like one capacitor for decoupling or bypassing because they're expecting most of the filtering to be done on the power supply side. I mean, you could put like a ton of capacitors everywhere, but then that just makes design harder. You need more space. Like,
yeah. And these would all be in parallel?
Yes, sorry. That was a huge thing I did not say. This applies when in parallel. Like capacitors add like this when they're in parallel. So our output filter will look like this.
Gotcha.
How is it that when you put the capacitors in parallel that you get a filter, like a better filter with less ESR? Like how is ESR connected to this?
So every capacitor has some ESR. So you could redraw this circuit like this.
Mm-hmm.
We want to minimize ESR because R, if you remember, the constant value is the limiting factor on this axis. So if our ESR is big, like the parallel sum of this, and this, if it's pretty big, then all of a sudden, the minimum impedance you could even achieve is like way higher.
I see.
So yeah, you look at the ESR value in your capacitor data sheet, and you're like, wow, this is huge. I don't want that. And some capacitors are better about like having lower ESR. Some of them have giant ESRs. It really depends on the type. And when we get into that, you get into what types of capacitors should we use? Should we use aluminum electrolytic? Should we use tantalum electrolytic? Should we use ceramic? And each of those have their own pros and cons. Like for ceramics, and sorry, I'm jumping into this, but like ceramics, you use them for small capacitance values, like microfarad size. Then if you need bigger capacitance values like millifarad, you go to aluminum electrolytic. But electrolytics are more finicky. They're more likely to break. They have like shorter shelf lives. They're susceptible to heat. But ceramic caps are more robust to all of these things. And you know, you're playing this game of cat and mouse where, again, you're trying to accomplish this red curve while also making sure that the capacitors will last long enough for like the shelf life of your product or what you're designing. What I'm trying to get at is there's a lot of things you have to consider when you're choosing your filter. It's not just a willy-nilly, let's throw 10 microfarads here, let's throw 0.1 microfarads here. Yeah. We could talk about something else for the next 3 minutes if y'all have questions about something we talked about today. If not, I want to try the same style as we did this week where I'll try to get you an assignment by Saturday night and then you'll have like a few days to work through it. And then hopefully we reconvene next Thursday and do some more learning. As for actual design work, from the way things are looking right now, with Olin's plans for opening and the probability of formula like being super active, I'd rate that pretty low. So we could take this at our own sweet time. So if y'all want to prioritize learning stuff, we could do that. But if y'all want to prioritize just starting making stuff, we could do that too. And that comes down to y'all. So like, what do y'all actually want?
I mean, personally, I'd like to learn the basics and like the foundations first before designing something.
Yeah, how much basics is there for the power supply stuff? Like how many more lessons?
I think we've honestly passed the basics. The basics, like if you knew what you got from the buck converter video, you could design a buck converter. Like that's all you really need. I think there's some cool stuff that we should be considering that we haven't as a team yet before, and that requires some learning on my part and y'all's parts.
Yeah, let's do that.
Okay. Yeah, because we know that we can make a buck converter that works. We want to make sure we can make a power supply that's good, like good enough for our sensing. Awesome. Well, thanks for joining, everyone. And I'll see y'all next Thursday.
Cool
Same
stuff.
time? Works?
Yeah.
Yeah.
Awesome. See you.
Enjoy your
Bye.